and then we'll get to the good stuff. All right. Thank you all so much for being here. Happy Wednesday. Good to see you. I see Aiden is in good spirits today. She's rocking her Santa Claus hat. I like it. Love it. Love it. Okay, so welcome back. Good to see you guys. Thanks for coming to hang out. A couple things that I wanted to mention before we jump into today's trig stuff. On today's announcement, I put a couple things on there that I'd like you to consider submitting to if you have the need. And I'm gonna start with the one at the very, very, very bottom of today's announcement, which I put on yesterday's announcement, but I forget if I had mentioned it. There's a spot there to drop any feedback for me if you feel that there's something that's either going well for you with remote learning or something that's not. Right? I've gotten both kinds of responses already so far. That's been really helpful. Whether it's you individually or as a group, if you feel like something's working or not working, just let me know. I want to always kind of refine my teaching, get better, and do the best I can for you as an individual or as a whole group. Or maybe there's something that a different teacher is doing that's really working for you that you'd want me to try on. I'm down to try it. So let me know if there's something like that. That's that very, very last link down there at the bottom. It's anonymous if you'd like it to be, or you can drop your name so I know it's for you. Either one's cool, okay? So that was one thing. The second thing is about halfway down today's announcement. There's a link that I included there for you to nominate a teacher or a staff member or both, counselors, secretaries, administrators, anything like that, for the Douglas County Apple Award for Ponderosa. Every high school, middle school, and elementary school awards the Apple Award based on the nominations of the students, parents, other teachers who feel like they have somebody that stands out. And this is not, don't get me wrong, this is not a plug for me, far from it. It's just that nobody really knows that this exists if we as teachers don't tell you to go do it. Because I think the people that know what's happening best in the classroom is you, right? You're the students. You guys are sitting there going through this, especially this year with hybrid and now remote. It's definitely a weird challenge for us as teachers. So I would love to have you put in a nomination, which is just a quick paragraph about why somebody has stood out to you, going above and beyond, or clearly doing something special here in the school to just make it as good as it can be. Whoever that may be, okay? If it's me, great. If it's somebody else, great. I just want your voice to be heard. Because right now there really aren't a lot of voices being heard in that realm. There aren't a lot of nominations out there yet. So there's a link right there. I'm gonna put it on basically every announcement from here until the final as a reminder for you. Sorry, I'm just reading something. Okay. To nominate, the teacher that you think is the best for you that you have this year, or a coach, or an advisor, or a counselor, or anything like that. Just a quick couple sentences about why they're so great. So that's when December 20th comes and goes, basically the end of next week, the team that makes that selection has a lot of nominations to go on rather than just one or two. And I think right now there's honestly there's only one or two on that whole list. So go and have your voice be heard, and let's award the people that are doing the best. So that's on there for you to do if you'd like. Obviously nothing required there for that Apple Award nomination. But it does mean a lot to whoever does win the Apple Award, and then they go on to, the next round where all of the winners go up against one another, I guess you could say, in a competition for the actual best high school teacher, best middle school teacher, best elementary school teacher, best staff member in the whole district, which is a really big recognition. So something to do if you'd like. It's completely optional, but something that we want to hear, who's doing a great job, and give them the recognition that they deserve. So that's there for you, okay? Today, let's get down to it now that I've said those two things. What I think we'd be best spent doing to start is just to kind of recap what we did yesterday. Right now, that stuff is stuck in your short-term memory, and I'd really love to transfer it to your long-term memory, because this will probably be something that we need to come back to, and I'd like it to be something that you get really comfortable with, right? Evaluating these trig ratios at unit circle values. So right below the link on the announcement that you clicked to get to today's meet, there's something that says click here for today's work for homework 4.2. Okay, and I'm calling it homework 4.2 because I do want you to submit your work by the end of the day today. My plan is to have us be done. We will have all of the work for this homework done before you leave class today. But I just want to give you some credit for doing all this work, and it also kind of give me an insight into how you're doing individually and also as a class. So if you click on that link, it'll take you to the assignments in Canvas, and then you'll click on the link within that assignment to open this up. The reason I made you do those double clicks is because now you see that there is a spot in Canvas where you'll actually upload this work by the end of today, okay? And then we're gonna start with these first 10 questions behind me, okay? Which are the 10 questions that are on there, and have a unit circle nearby, right? Always. And so I included a link for both completed ones and blank ones, again. But you can pull up the stuff that you did yesterday and give yourself an understanding of how to get these done, remembering that cosine is x, sine is y, and every other trig ratio is just some relationship between those two, right? Whether it's tangent and it's y over x, or you've got the reciprocals of all three of those, okay? So I wanted to just give you, I mean, it's 10:30-ish right now, give you like 5 or 10 minutes and see how well you can do. I'm gonna start putting up solutions to these behind me. And by the end of class today, I will upload all of that work as well, so that you can take a look and make sure you're doing okay. But take some time, take out a piece of paper and open up this homework 4.2 and let's just try this part one. Just a quick refresher from yesterday on evaluating trig ratios at really nice unit circle spots. Okay, so I'm gonna let you work and ask questions if you have any, and we'll go from there. Cool. So there is my 10. I'll give you another few minutes. Let me know if you have questions. Oh, that makes it worse. Hopefully you can see that okay. Things were a little blurry yesterday, so let me know if you need me to read anything or talk through anything. Oh, a couple minutes.
Is that top number 1, is that the square root of 2 over 2?
Yes, number 1, square root of 2.
Thank you. No worries, Gracie. No problem. I know my Wi-Fi at home is so bad, which is why I almost never live stream from home. So I totally get it. Even from here, the Wi-Fi can be a little spotty from time to time. So it's all good. That's why I try to record everything. You can always go back and watch videos if you need anything. Plus, you can skip all my my chatting that happens in between the two. So. Have a couple moments should you need it. Hopefully this stuff is coming back to you a little bit from yesterday. Cosine being x values along the unit circle at those spots, y values being sine. And you see that I only had 1 degree measure, right? Most of what we're going to do is in radians, so good to keep in mind. We'll bounce back and forth though, for sure. 4 we have to rationalize. 10 we have to rationalize that denominator. Number 6 we end up dividing by 0, so that's undefined there, so that's no good.
And then kind of the three versions of tangent and cotangent with 8, 9, and 10. 8, things working out really nicely at a multiple of 45 degrees, one of those angles that have the same x and y value, just sines all we have to care about, right? So that worked out really nicely. 9, where you're at a multiple of 30 or 60, it could work out where you don't have to rationalize, or it could work out where you do. And those are really the only possibilities at those spots, are either radical 3 or 1 over radical 3. And then, of course, we'll rationalize to radical 3. And in just a couple moments, I will switch over to the next thing that we're going to do. I'll switch over to the other whiteboard. And I'll just show you this one thing today. I got one more idea that ties in nicely with this that I'm pretty sure is new to you in at least a little bit. It might be brand new, which is always good. So that'll be coming next. And then we'll just meet back one more time tomorrow just to kind of wrap things up a little bit. I'm bouncing around chapter 4. And I'm calling this homework 4.2, but there's some 4.2 stuff in here. There's some 4.4 stuff in here. 4.4 is really trig ratios of any angle in any circle. And that's the ratio setups I gave you with the x over r, y over r, y over x. That's 4.4. It just makes a whole lot of sense to start with that, and then we can apply it to the unit circle where r is 1, right? But knowing those trig ratios are set up the way they are in 4.4 is really nice that way. 4.3 gets into right triangle trig. So maybe not nice unit circle numbers, but really nice side lengths. Thinking about like Pythagorean triples like 3, 4, 5 right triangles. We'll talk about those tomorrow. Because that definitely comes up too. Where the angle measures maybe aren't so nice, but the side lengths are really, really, really nice. This square root of 2 stuff. Hopefully you're good at this point. How'd you do? Was that okay? You feel like you've got a pretty good sense of how this is going? Sweet, awesome. See some thumbs up. Appreciate that. Okay, cool. Let's do it then. I will try to get you out of here on time today. All right. So what I want to do is switch over to here and start talking about what we're able to do now that we have a really good understanding of how to deal with trig stuff. Okay, so let's see, where does the glare begin? Kind of like right there. Okay, so what we've done kind of up to this point with trig is that we have been given an angle, right? And of course, they have to tell us what the trig ratio is for that angle that we care about. But they give us an angle, and our job is to find the ratio. Right? Given an angle, we find a ratio, a single ratio, right? That does a job. And maybe that ratio is radical 2 over 2, or maybe it's square root of 3, or maybe it's 1/2, or maybe it's undefined, or 0, or whatever, right? We've got a setup that, like, we're given something and we're able to find something else, right? We've got these trig ratios, but they're really starting to happen in a certain order, right? We're given one thing and we're able to find another. And that kind of starts to remind us of the way that functions work, right? You give me an x, I'll give you the y that goes with it. And that's really what we're dealing with here, right? We're given some input, and we are able to find an output, right? We're given some x, I'll tell you the y that goes with it. It's just that we're not really dealing with x and y necessarily, right? We're dealing with angles, right? We're dealing with some theta values, right? And what we're able to do is then give you an f of theta that goes with it. Right? And those functions you're going to see are these trig ratios, right? So I could have the function sine of theta, the function cosine of theta, the function cotangent of theta. They're all unique trig functions, which is what we're kind of building up towards. But what I wanted to make sure that we're understanding is that we can do the opposite as well. we can be given a ratio. And of course, you have to tell me which ratio we're looking at. Is it a sine ratio? Is it a cosine ratio? Is it a tangent ratio? Whatever. And so I want to hear from you. So unmute yourself if you've got a good response. You think, if we're given an angle, we can find a ratio. Well, if we're given a ratio, and again, I tell you if it's sine or cosine or whatever, but I say that the sine of that is 1/2, or the cosine of that is 0, or the tangent of that is undefined, or something like that. What do you think we should be able to find based on what was given?
An angle?
Nice, good. And here's the thing, we might be able to find more than just one angle. So it might not just be an angle, it might be angles. All right, because there could be more than one spot along the way where we get a certain ratio back, right? Cosine of an angle could be 0 at like pi/2, because x is 0 up there, or 3 pi/2, okay? But you see how things are switching, right? Our x's are y's, our inputs or outputs, they're flipped, right? I'm taking x and y, I'm taking theta and f of theta, and I'm switching them. What is that called when we deal with functions that, okay, give me an x, I'll give you a y. Well, what if I switch that? What do we call that relationship now?
Inverse.
Awesome. Okay, so we have kind of regular trig ratios, but we also have inverse trig ratios. Okay, and these buttons are on your calculator as well. Okay, so if you have your graphing calculator, Neil Bryan, I'm going to show you a little bit in the calculator too, so you can see it. You've got sine, cosine, and tangent buttons only. I don't need a secant button because that's just 1 over cosine, right, and so far. But you do have these buttons on your calculator, like second sine, second cosine, second tangent, that have that little -1 up there at the top, okay? And all of those are going to be your inverse trig kind of button. So for example, you've got like sine with that little -1 right there. Now, it's not an exponent of -1, it's the symbol for inverse. And so what's going to happen is normally right in here, if it was regular sine, we drop an angle, right? Sine of 30 degrees, cosine of pi/4 or whatever, right? Well, no, that's not what's going to go in now. That's what we're going to get back. The result from inverse whatever is going to give me an angle. What's going to go in here is whatever that ratio is, okay? And when I'm talking about ratios, I'm talking about the radical 2/2s, the 1/2s, the radical 3/2s, the zeros, the ones, all of their positives and negatives that we could find as answers along the way from the unit circle. Now, sine and cosine are definitely the easiest inverse trig ones to do because we're just looking for x or y. And so all we'll have to do is look for spots on the unit circle that get us there. So let's do it. Let's actually try some of these out. Go back to that homework 4.2. Okay. Pretty soon my little secrets of keeping these follow-up parts written in white probably won't surprise me anymore. But there's a little part 2 there. Can anybody read that backwards? Oh, I spelled it wrong. Oh, hold on. There we go. Inverse trig, let's go backwards. And that's all we're going to do, okay? We're going to try to figure out what that looks like, okay? Now, so here's what I want to try to do. I want to walk through these 6 with you so you get a sense for how to do these. And that'll give you a little practice on how to get it done. But the setup is that they're going to tell us a trig ratio, which one, sine, cosine. And we'll just start with those to begin. And then all we're looking for are all of the angles that get that ratio back, were we to plug it in. Okay, now here's the thing that we want to make sure we're doing. We want to kind of restrict our answers to a certain space, okay? Because we could take trip and trip, like trip after trip after trip around the circle, and we keep ending up at the same spot, right? I could go 0 degrees, where's 0? This side. I can go 0 degrees, or 2 pi, or 4 pi, or 6 pi, or 8 pi, and I keep ending up at that same terminal spot. I don't want to list an infinite number of answers whose cosine is 1, right? That's not very interesting to me. Usually what we'll do is our answers to inverse trig type problems will be restricted down to a certain space, a certain set of answers, okay? And it depends on what we've got, and we'll dive a whole lot deeper in inverse trig probably in January. But for now, all I want to do is just stick within one trip around the unit circle, okay? So from 0, and I'm going to include that, okay, to 2 pi, but I am not going to include that because that's the same thing. 0 radians and 2 pi radians are the same angle. So I don't want to be too repetitive in the solutions that I write down here, although there are an infinite number of possibilities for the cosine of 1, right? The cosine of some angle giving me 1, 0, 2 pi, 4 pi, and so on. And negative 2 pi and negative 4 pi, right? Because we can open up positive angles and we can open negative ones. All right, let's give it a shot. All right, so number 1. And read that out loud as inverse sine of 1/2. And so I want to hear from you. Your job now is to take a look at that unit circle, okay? And find an angle whose sine value is 1/2, okay? And I think the best way to do that, so that we write our solutions in a good order, is to start at 0 and start opening up positive angles that way and check all of the options between 0, not my best circle, and 2 pi. Okay? And we're going to list them in that order. The ones that we encounter first, then second, then third, then fourth, because there could be 1, there could be 2 answers, there could be 3, there could be 4, there could be none, right? Take a look. Because it's sine, we're looking for y values. Okay, if they were asking for cosine, we'd look for x's. And all I want to do is find a y value that's 1/2 and write down the angle in radians. That got me there. Find me the first one that you run into as you open up a positive angle.
Pi over 6.
Awesome. Pi over 6 works. Okay. Is there another angle between 0 and 2 pi that also has a y value of 1/2?
5 pi over 6.
Absolutely. And so there are actually 2 solutions to this setting. Okay, and that's not uncommon, right? Because think about it, we're looking for y values that are the same. And so if I'm looking for a y value that's 1/2 and I find one over here, let's say, so here I am on space, well, if I just go straight across from that, my y values aren't changing and I run into the circle again, right? If you draw a circle and you start moving a horizontal line up and down, so keeping the y value the same at a certain point once we stop, you're going to hit that circle probably twice most of the way, right? The only time you'd ever hit it once would be up at 1 or down at -1. The only time you would ever hit it 0 times would be above 1 or below -1, right? Good, so there you go. All right, so that's what that looks like. And that's all we really have to do with things like 1 through 3, right? Okay, so number 2, the inverse cosine of -1/2 is the question that they're asking. And so what I want your mindset to be is that, okay, if I'm given a ratio, right, with inverse trig, I'm looking for an angle. And I want to open up an angle, a positive angle, and see all of the answers that fit the bill. All of the ones that are going to give me, in this case, an x value, because it's cosine, of -1/2. Tell me when you find one.
Two pi over 3.
2 pi over 3. Is there another one?
7 pi over 6.
That would be a y value of negative 1/2. We want the x because they're asking for cosine.
4 pi over 3.
4 pi. And what you'll notice, if you look at the unit circle at both of those spots, they are right on top of each other, right? Because the x value is the same. So I'm just kind of looking for a spot that, okay, if I find an x value here that works, well then if I just drop something straight down or up from wherever I am, and I hit the circle again at that spot, then the x value shouldn't change, and I should have another solution that works, okay? And so most of the time, you're gonna find two possibilities for these kind of angles, the 1/2s, the negative 1/2s, the radical 3s over 2s, the 2s over 2s, the ones that are inside a quadrant somewhere. The quadrantal angles might only have one, but they could also have two. So we want to kind of watch out for those as well. But look, divided by 6, divided by 6, divided by 3, divided by 3, that's not a coincidence there. That those kind of angles are the ones that are showing up twice. They're going to have the same denominator most of the time. So you can feel pretty good about that. Okay. Back to inverse sine for number 3. This one, negative radical 2 over 2. So are we looking for x here or are we looking for y?
Y.
Good. Sine, right? Sine is y. All right. Cosine is x, sine is y. So find a y value on the unit circle. And we'll write them in a good order. We'll go from the beginning, just kind of work our way. That has a y value of negative radical 2 over 2.
5 pi over 4.
5 pi over 4 works. And
7 pi over 4.
good. 7 pi over 4. No big surprise here, both being divided by 4. Okay. Awesome. You got it. That's the basics when it comes to inverse trig. Now, the thing that I want to make sure you understand about what's going to happen in the calculator is a little bit different than what happens when we go back to regular trig. Because if I'm given a certain angle in trig and I'm finding a ratio, I can only ever find one because I'm stopping at a certain spot and I'm just looking for x or y or some ratio that goes with it, right? So I'm always going to get myself an angle. And the calculator can do that for us, right? I can drop in sine of 30 degrees or sine of pi over 6, depending on what mode I'm in. Let me actually do this now since I'm talking about it. I want to show you my graphing calculator, okay? And what you can do with a graphing calculator to do all of this trig stuff, okay? So in my graphing calculator, right, sine, cosine, and tangent are all right here. There are the inverses that go with them, but next to the second button is mode. Okay, and you've got options to be in either radians or degrees. And you got to make sure that you're doing what you mean to do. That if I'm in, let's say, radians, okay, and I type in something like sine of 30, well, sine of 30 degrees is 1/2, but the sine of 30 radians is definitely not, right? Because that's not 30 trips around the circle. Remember, a radian was only, is the length of an arc that's equal to the length of the radius in that circle that you're in. And so things don't work out really nicely that way. So if you want to do sine of 30 degrees, you better make sure that you're in degrees when you do that, so you get yourself an answer that looks and feels a whole lot more correct, right? And so, but when I do that with inverse trig, let me go back to radians for a second. If I type in the inverse sine of 1/2 and I'm in radians, I'm not going to recognize fractions like pi over 6.
That's pi over 6 right there. Pi over 6. I have no idea what pi over 6 is, or what pi over 3 is, or 2 pi over 3, or 7 pi over 6. Like those fractions as decimals, I have no idea. And so when I'm doing inverse trig, I'm a big fan of using degrees, because then when I do something like the inverse sine of 1/2 and I get 30, I feel a whole lot better. But here's the thing. No matter how many times I do that, I'm always going to get 30 degrees. I'm always going to get pi over 6. I'm never going to get 5 pi over 6 because of the way that the calculator works. And I just wanted you to understand what's happening. So this is what we should do when we're doing inverse trig. Here's what the calculator, I'm going to stop sharing for a second so it's a little bit bigger. Here's what the calculator does, okay? When it does an inverse trig, what the calculator does is it doesn't open up one positive angle, okay? It opens up a positive angle and a negative one at the same time. Okay, the calculator is cutting its processing time in half by doing twice the work, and it's going to look for the first answer that's correct. And then it stops looking. And that's what's happening here, right? When it stopped at 30 degrees right there, it was happy, right? And it's never going to keep going and make its way all the way to 150 degrees. And it's certainly not going to get to negative 210 degrees by opening up a negative angle at the same speed that it opens up a positive. Okay? And so what I want you to realize is that as nice as the calculator is, it's a little bit incomplete. And it's not necessarily going to work as well as we might want. Because if I asked the question, hey, what's the inverse sine of, hey, like negative radical 2 over 2? Let's do that one. I like that one. Okay? When it opens up angles in the positive direction and the negative direction, the first one that it's going to run into is that one right there at 7 pi over 4, right? It's not going to get to 5 pi over 4 by going all the way around this way first. It's going to get to 7 pi over 4, but to do that, it's going to get there in a negative direction. And it's going to give us negative 45 degrees. Not 315, but negative 45. So you just want to be really careful. Okay, so I just wanted to make sure you knew why the calculator was doing what it's doing. This is what happens. It opens up two angles, a positive one and a negative one, and it gives you the first angle. Now, if it ran into both at the same time, it'll give you the positive one, which is nice. So if you open up an angle this way and you're finding like cosine of, an inverse cosine of 1/2, it'll give you the pi over 3 before it gave you the 5 pi over 3, right? The negative pi over 3. So that's good. Okay, cool. Sweet. Again, let me just share because I know I said it. I want you to see what my calculator just did when I opened up a negative. Okay. The inverse sine of negative radical 2 over 2, it gave me negative 45 degrees. Again, I'm always in degrees when I'm doing inverse trig, and then I'll do the conversions so I can get those answers. Okay, here we go. Let's finish up. Number 4 is where things start to take a little bit of a turn. Oh, what am I doing? Oh, I deleted it. Okay, I was like, where did it go? There we go. Okay, number 4 is where things start to turn a little bit. Inverse cosine of 1. X values, because it's cosine, that are 1 in this interval that includes 0 but does not include 2 pi. What do you get? Can you find an x value, cosine, that's 1 on the unit circle somewhere?
5.
Say that again, sorry. An x value, that's 1. I'm listening. I got to charge my laptop.
It's 0, right?
0. Yeah, exactly. Because when we first start, right, when we go to that beginning spot on the unit circle, the x value over there is 1, right? Because that's the 0.1 comma 0. And so the only spot that works is 0 because the other one will be 2 pi, and we're not going to include that, right? I don't want to say the same thing twice. Okay, so most of the time we'll have 2, but it is possible that we only have 1, but that would only ever happen at a quadrantal spot. Okay. How about the inverse cosine of 3.5? Can you find a spot on the unit circle where the x value is 3.5?
No.
Me neither. Because it doesn't exist. Because unit circle is stuck between -1 and 1 for x and -1 and 1 for y, right? Now, when I think about, let me see how I can write this best. Maybe I'll put it over here. When I think about just like plain old sine and cosine, sine of theta and cosine of theta, the domain of those kind of functions are all real numbers. Right? I can plug in whatever angle I want, and I'll get a number back. But the kind of numbers I can get back are only ever going to be between -1 and 1, right? Because sine is y and cosine is x. And when I'm stuck in the unit circle, those are the only possibilities that I have. And so when I start to deal with the inverse of each of those, just like x and y switch with inverses, so do domain and range. Okay? And so what happens is my domain, the possibilities that I have of what to plug into an inverse function, I am stuck with options between -1 and 1 for sine and cosine, right? Because those are just x and y values. Now, I know I said that the range would switch and that it could be all real numbers, but the problem is we wouldn't get ourselves a function if we did that. So I'm going to put all real numbers here, but I'm putting an asterisk next to that because what we are going to do, just like the answers to our inverse trig problems are going to be restricted to, to a smaller space, we are going to restrict the range to deal with functions instead. Because if we didn't, this is what the graph of inverse sine would look like. Bro, it would just be kind of this wiggling vertical wave. And so eventually what we will do is we will chop it to a space where it's just a function. And we'll deal with that in January. But really, really important to know that we can't just plug in any number we want into inverse sine and inverse cosine. Cool. I think there was one more. Ooh, this is a good one. A little challenge here for you. Inverse tangent of 1. All right, well, think about what that means. Sine is y, cosine is x, tangent is y over x. Okay. And so if you were giving me an angle and you asked me for tangent, then I would give you the ratio of y over x. Well, this is going the other way, right? Inverse tangent is giving us the ratio. And our job is to find an angle or a set of angles that does that for us. And so what this challenging question does is it kind of puts you to the test a little bit to understand a couple things. Number one, what we're looking for here is an angle whose tangent is 1. Right? That's what we're looking for. Our answer will always be an angle or a set of angles. But to do that, I have to think about what kind of angles would have tangent values of 1. And if tangent is the fraction y over x, and the answer to that fraction is 1, well, then what do you know about the numerator and the denominator of a fraction if when I divide those two, I get exactly 1?
They're the same.
gotta be the same also, right? Because I've got a fraction, y over x. And the answer that I'm getting is 1, which means what we're looking for on the unit circle is an angle or a set of angles that have the exact same x and y values. There are 2. Fine.
Pi over 4 and 5 pi over 4.
Awesome. Okay. We know that at multiples of 4, right, 45 degrees, right, denominators are 4. We're looking at that radical 2 over 2, radical 2 over 2. We just have to watch our signs, right? Here in the first quadrant, everything's positive. Here in the third quadrant, everything's negative, and so the negatives would cancel too. There you go. Okay, I could go a whole lot crazier with inverse cosecants and secants, but I'm going to keep it fairly simple for us with inverse trig stuff. Again, I'm taking about like a 6-week trig unit here to give you as much knowledge as I can that's useful without kind of overstretching you. So there you go. Okay, there's inverse trig right there. Really helpful to know these domains and ranges and stuff. That'll come back for sure for us. And also really nice to know what's happening in the calculator so that you don't rely too much on it. Now, if you're stumped, yeah, look at the calculator, right? Type in inverse whatever and see what you get. And I bet if you typed in inverse tangent of 1 and you were in degrees so you could recognize the answer, you'd get 45, okay? And then you could just use that to help you look for the next one. Okay. Sweet. Here's the last part that I just want to give you a chance to try. There it is. So go back to the homework 4.2. There's a part 3. Now you can see why I stay up till midnight writing things, because I have to write stupid little backwards sentences to entertain myself, and maybe even 1 or 2 of you guys at home. 7 through 14 there, to see if you can do it. Okay, can you handle inverse trig evaluation? Okay, looking for 1, maybe 2 angles, or none. Right? If there's none, okay, undefined. That's okay. Right? Because it's outside my domain, and if we're outside the domain, we are undefined at that spot. It's not that it's no solution. We're not solving an equation, right? There was no equal sign to start. Right? You're just evaluating. So we're undefined. Okay? So try those. Let's see, 7 through 14 would be 8 questions. And when you're done, submit that work to that assignment on campus. Okay? I'm going to erase my work over there and put up some solutions so you can see them, so you can see how you're doing. So stick around if you'd like. Otherwise, finish those up at your leisure today and get that submitted. Might as well stick around. We have a couple minutes. Might not take you more than a couple minutes to use that unit circle. But again, reminder, if you have any feedback from me specifically, go to the bottom of today's announcement, and I'll kind of post it all week and next week as well. And send me some either anonymous feedback or put your name on it if you want. And definitely, if you have somebody in mind that you think is deserving of the Apple Award, nominate them. Okay, it goes a long way to hear the voices of students. Okay, and you can do a video nomination. You can just kind of record yourself saying a few things about somebody, or you can just type it up. And the link is right there for Ponderosa. Okay. We appreciate that. We want to hear who's doing great. Mr. Warburton won it last year, I think. Super deserving. Mr. Warburton is the man. If you have not taken a class with him, do it. Right? You're missing out on one of the best teachers in the school if you don't take a class with him. I think Mr. Huff won it the year before. Super deserving. Right? Works his butt off. So do it, right? Nominate somebody that you feel is deserving. Okay, I'm gonna take this over to here and write down my work for 7 through 14. I will post those solutions to Canvas so that you can always go back and take a look. Should you want to? But hopefully you're feeling really good. Hopefully this stuff is clicking for you. My guess is a lot of this stuff is relatively new, if not completely new for a lot of us, which is good. And that's what I want to do. I want to get to new stuff. I might try to redesign this class next year so that it's less review and more new stuff. I don't know. And that's the kind of feedback that I'd love to hear from you by the end of the year too, is what worked and what doesn't? What do you need and what don't? Should I do as much with chapter 1 and chapter 2 that I did, and or should I skip some of that and spend more time on the new stuff? I don't know. I'm always trying to get better, so help me do that. Inverse cosine. Do those first. 2, 6. Inverse -1/2. Did we do that one? Oh, we did positive. 7, 6. You can see, I'm using those, those set notation brackets because I'm listing more than one answer, right? You have a set of solutions, always good. If you wanna also put it for your singletons, that's a little redundant, but hey, go for it. If not, that's cool too. And hey, if you don't include it and you just list them, that's fine too, no big deal. The set notation is just kind of a nice thing to draw there. That's 7. I wonder if that 7's up to that. 7 is pi over 6 and 11 pi over 6. All right, I'll drop down a little bit lower. 11.
Wait, Rosie, for number 1, isn't it negative root 3 over 2? Radical 3 over 2?
For which one?
For number 7.
Number 7 is positive root 3 over 2.
Thank
So,
you, I'm blind.
Number 7, cosine of negative. So the inverse cosine, number 7, inverse cosine of radical 3 over 2. So I'm looking for x values that are positive. So that's going to happen in the first quadrant and the fourth. Pi over 6 and 11 pi over 6.
Thank you.
Okay. 14, obviously a nice little challenge there, but use number 6 from before to help you with that. It can't be bigger than 1 or less than negative 1. Number 12. Very cool. So there you go. There are the solutions to that. Stick around and work through those if you don't have any place you need to be.
Thank you.
Thank you. See ya.
Thank you.
Bye. Thank you.
Have a good day.
Thanks. See you tomorrow. I'll come back on for tomorrow. We'll do one last day.
Could you go over 9 really quickly?
Sure, I'd love to. Okay, so number 9 is, oh, that's wrong. Maybe that's why. Pi over 4 and 7 pi over 4. Sorry about that. So inverse cosine of radical 2 over 2. So I'm looking for an x value that's going to give me a radical 2 over 2. So that happens at 45 degrees and 315 degrees, or pi over 4 and 7. So
Thank
pi
you.
over 4, yeah, sorry.
Thank you.
Thanks, see ya.
Can you go over number 12?
Sure. Okay. So let's see. Hopefully I didn't make a mistake there. Okay. So number 12, inverse cosine of negative radical 2 over 2. Okay. So negative radical 2 over 2 is the x value that we're looking for. And so I just kind of look at my unit circle and I'm looking for an x value that's negative. So if an x value is negative and I'm on a graph somewhere, I want to be to the left of the y-axis. So I'm looking like second quadrant and third quadrant for angles that are going to give me this kind of fraction. And the radical 2 over 2s are always going to happen at those multiples of 45, those multiples of pi over 4. Okay? And so 3 pi over 4 and 5 pi over 4 should be the radian measures whose x value is negative radical 2 over 2.
Thank you.
You're welcome.